Max Planck's role in the birth of quantum theory stands as one of the most transformative moments in the history of science. Planck, a German theoretical physicist, was not only the first to introduce the fundamental principles that would eventually give rise to quantum mechanics, but also the one who, with his groundbreaking work, changed the way we understood the very nature of energy and matter. His work, particularly his discovery of energy quanta in 1900, opened the doors to an entirely new realm of physics and established the foundation for what would become the quantum revolution. The story of how Max Planck came to develop the first quantum theory begins with the problem of blackbody radiation. Blackbody radiation refers to the electromagnetic radiation emitted by a perfect blackbody, an object that absorbs all incident radiation and re-emits it. In the late 19th century, scientists were baffled by the so-called ultraviolet catastrophe. According to classical physics, the laws of thermodynamics and electromagnetism predicted that a blackbody would emit an infinite amount of radiation as the frequency of the emitted radiation increased. This problem led to a paradox because, in reality, blackbodies did not emit infinite radiation. They emitted energy in a predictable pattern, one that scientists had yet to explain. Before Planck's involvement, the classical theory, which was based on Maxwell's equations for electromagnetic radiation, had failed to explain the observations related to blackbody radiation. The classical approach, known as Rayleigh-Jean's law, predicted that as the frequency of radiation increased, the intensity of radiation would rise without bound, leading to infinite energy output, which was clearly at odds with experimental results. This was a monumental failure because the experimental results showed that the intensity of radiation actually peaked at a certain frequency and then decreased for higher frequencies, which is what we now know as the blackbody radiation spectrum. Planck, tasked with solving this riddle, faced a daunting challenge: how to reconcile the predictions of classical physics with the reality of experimental observations. Planck's approach was both bold and ingenious. Rather than relying purely on the principles of classical physics, he introduced a revolutionary idea that energy was not emitted continuously, but in discrete units or quanta. This idea was revolutionary because, at the time, energy was believed to be a continuous quantity that could take on any value. The prevailing view of the time, following the principles of classical mechanics, was that energy could be measured and emitted in a smooth, continuous manner, much like how water flows in a continuous stream. However, Planck proposed that energy could only be emitted or absorbed in discrete amounts, and these amounts were proportional to the frequency of the radiation. This concept was first introduced in 1900 when Planck was trying to find a mathematical solution to the blackbody radiation problem. Planck's equation, which is now known as Planck's law, provided an accurate description of the observed spectrum of blackbody radiation. However, the key to his success lay in his introduction of the concept of quantization of energy. Planck postulated that the energy of the oscillators in the blackbody was quantized and that the energy levels of these oscillators were restricted to specific values that were integer multiples of a basic unit of energy. This unit of energy, which he called a quantum, was proportional to the frequency of the radiation, and the proportionality constant became known as Planck's constant, symbolized as h. The breakthrough idea behind Planck's theory was that energy was not a continuous quantity, but rather discrete packets of energy. He introduced the idea that the energy of a system could only exist in these quantized states, which had to be an integer multiple of a fundamental quantity. The importance of this assumption cannot be overstated. By suggesting that energy is quantized, Planck offered a solution to the ultraviolet catastrophe and aligned the predictions of his theory with experimental data. His formula not only explained why blackbodies did not emit infinite radiation at higher frequencies, but also accurately matched the observed spectrum of radiation emitted by heated bodies. Planck's constant, which he derived from his equation, became one of the most important constants in all of physics. It marked the beginning of quantum theory by showing that physical systems at microscopic scales, such as atoms and molecules, behave in fundamentally different ways than macroscopic objects. The constant itself, a tiny value at the scale of everyday objects, took on a huge significance in the quantum world. Planck's constant became the central feature in the development of quantum mechanics, and its introduction marked the birth of a new era in physics. However, Planck's discovery was not immediately embraced by the scientific community. His idea of energy quantization was so radically different from the classical view that it was met with skepticism. Most physicists at the time were unable to accept the notion that energy could be discrete, as it contradicted the established understanding of energy as a continuous quantity. Even Planck himself was initially reluctant to fully embrace the implications of his discovery. He believed that his theory was merely a mathematical trick, a means to solve the problem of blackbody radiation without necessarily implying that energy was truly quantized. But as experiments continued to confirm the validity of his formula, Planck's theory slowly gained traction among physicists. In the years that followed, Planck's work provided the foundation upon which other key developments in quantum theory would be built. Albert Einstein, for example, used Planck's quantization idea in his explanation of the photoelectric effect in 1905, which further cemented the concept of energy quanta. Niels Bohr, building on Planck's work, developed his model of the atom, which also relied on the quantization of energy. These developments, along with contributions from other physicists, such as Werner Heisenberg and Erwin Schrödinger, eventually led to the full-fledged theory of quantum mechanics. Max Planck's contribution to the field of physics was transformative. His work on blackbody radiation and the quantization of energy opened up a whole new world of inquiry that would forever change the landscape of science. Planck's constant, a simple number that defines the scale of quantum phenomena, became one of the cornerstones of modern physics. His discovery heralded the beginning of quantum mechanics and set the stage for the development of new technologies that rely on quantum principles, such as semiconductors, lasers, and quantum computers. Planck's work, though initially met with resistance, is now recognized as one of the most important milestones in the history of science. The impact of Planck's work extended far beyond his own time. The ideas that he proposed have continued to influence the development of physics in profound ways. His discovery of energy quantization was a pivotal moment that helped shift the direction of physics away from classical mechanics and towards the strange, counterintuitive world of quantum mechanics. It allowed for the development of a new framework for understanding the behavior of particles on the smallest scales, a framework that continues to shape our understanding of the universe today. Max Planck's role in the birth of quantum theory is a testament to the power of human curiosity and ingenuity, and his legacy continues to inspire generations of scientists who seek to uncover the mysteries of the quantum world. Max Planck's introduction of the first quantum theory was more than just a mathematical breakthrough. It was the beginning of a seismic shift in the very foundation of physics that would eventually unravel some of the deepest mysteries of the universe. While his initial discovery was made in response to a specific problem in blackbody radiation, it led to a series of developments that reshaped our understanding of the physical world on a fundamental level. In the decades following Planck's 1900 discovery, the idea of quantized energy, though initially controversial, gained increasing acceptance, and the broader implications of quantum mechanics began to unfold. To understand the magnitude of Planck's contribution, it is important to recognize that the world of quantum mechanics is vastly different from the classical world we experience in our everyday lives. Classical physics, which had dominated scientific thought for centuries, was based on the idea that physical quantities such as energy, position, and momentum could vary continuously. Planck's theory, by contrast, was the first to introduce the radical idea that these quantities were discrete at the microscopic level. Planck's work on energy quantization provided an elegant solution to the problem of blackbody radiation, but its significance extended far beyond that. The concept of quanta suggested that the laws governing the smallest particles, atoms, and subatomic particles were not governed by the same smooth, continuous laws that we observed in macroscopic systems. In essence, Planck had introduced a dual reality, one where the behavior of large objects could still be described by classical physics, and another, hidden from direct view, where quantum mechanics reigned. The philosophical and conceptual implications of Planck's discovery were profound. The idea that energy could only exist in discrete packets raised questions about the nature of reality itself. If energy could only be released or absorbed in fixed amounts, what did this mean for the behavior of particles and atoms? How could these tiny, quantized units of energy give rise to the vast and seemingly continuous world that we observe? These were questions that would shape the development of quantum theory and lead to deeper philosophical debates within the scientific community. At first, Planck himself was reluctant to embrace the full implications of his own work. He saw his formula as a mathematical expedient, a temporary fix to the problem of blackbody radiation, rather than as a fundamental insight into the nature of the universe. However, as more and more experimental evidence emerged to support his theory, Planck began to realize that he had stumbled upon something much more significant than a mere mathematical tool. His work was the opening of a door to an entirely new way of understanding the microscopic world, one that would eventually evolve into the theory of quantum mechanics. This theory would later be expanded upon by other prominent figures in physics, including Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein, for example, used Planck's idea of energy quanta to explain the photoelectric effect in 1905, further cementing the concept that light itself, which was once thought to behave only as a wave, could also behave as a particle. This discovery was a crucial step in the development of quantum mechanics. Bohr, building on Planck's work, developed his model of the atom, which proposed that electrons orbit the nucleus at specific energy levels, another manifestation of the quantization of energy. These ideas, along with Planck's constant, became the foundation for the development of the full quantum mechanical model of the atom. One of the most revolutionary aspects of Planck's theory was that it suggested that the universe, on its most fundamental level, was not continuous but discrete. This was in direct contrast to the classical view, which held that the properties of matter could take on any value within a given range. In the quantum world, however, particles and energy could only exist in specific, quantized states. This idea had far-reaching consequences not just for physics, but for our understanding of reality itself. The concept of energy quanta introduced a level of uncertainty into our understanding of the physical world, as particles no longer followed the smooth, predictable paths described by classical mechanics. Instead, their behavior became governed by probabilities and wave functions, leading to the creation of the uncertainty principle, later formulated by Heisenberg. Planck's discovery also set the stage for the development of entirely new technologies that rely on the principles of quantum mechanics. The most immediate consequence of Planck's work was the development of quantum theory, but it also had practical applications that would revolutionize the technological world. For example, the advent of semiconductors, lasers, and magnetic resonance imaging, MRI, was all made possible by the principles of quantum mechanics that Planck helped establish. Today, we live in a world where technologies like computers, smartphones, and lasers all rely on the principles of quantum physics. Furthermore, Planck's work had profound philosophical implications. The idea of quantization challenged the classical view of a continuous, deterministic universe. It introduced the concept of uncertainty and probability, where the behavior of particles could only be described in terms of statistical probabilities rather than certainties. This was a sharp departure from the determinism of classical physics, where the future of a system could be predicted precisely given its initial conditions. In the quantum world, uncertainty was not just a limitation of our knowledge, but an inherent feature of reality itself. The advent of quantum mechanics thus raised deep philosophical questions about the nature of reality, the role of the observer, and the limits of human knowledge. The resistance to Planck's ideas during his time underscores just how radical his theories were. The early 20th century was a period of intense scientific revolution, and the transition from classical to modern physics was anything but smooth. Many scientists initially rejected Planck's idea of energy quantization, as it appeared to violate the principles of classical physics. However, over time, as more and more experimental results confirmed Planck's predictions, his ideas gained acceptance. By the 1922, the development of quantum mechanics had become a central part of the scientific landscape, and Planck's ideas were recognized as the foundation of this new theory. Planck's legacy, therefore, is not just in his theoretical contributions, but in the way his work paved the way for future scientific breakthroughs. The ideas he introduced were the spark that ignited the quantum revolution, which, in turn, led to the development of modern physics. His work continues to influence not just the field of physics, but also our broader understanding of the universe. In the quantum realm, where the rules of classical physics break down, Planck's constant remains a fundamental feature of the universe, guiding our understanding of the smallest particles and the forces that govern their behavior. In conclusion, the birth of quantum theory, which began with Max Planck's work on blackbody radiation, marked the dawn of a new era in science. His introduction of energy quantization was a breakthrough that forever changed the landscape of physics. Though initially met with resistance, Planck's ideas formed the cornerstone of quantum mechanics, a theory that has reshaped our understanding of the universe. The implications of his work continue to be felt today, as quantum mechanics drives the development of new technologies and deepens our understanding of the nature of reality. Max Planck's contribution to science, though initially underappreciated, has since proven to be one of the most important discoveries in the history of human thought, laying the groundwork for the quantum age and shaping the modern scientific worldview. Max Planck's work on blackbody radiation and the introduction of the quantum theory represents a pivotal moment in the history of science. One of the most significant aspects of Planck's work is his explanation of the behavior of blackbody radiation, a problem that had stumped physicists for years. The blackbody radiation problem was not only crucial for understanding how heated objects emitted energy, but also for bridging the gap between classical and quantum physics. Planck's approach and subsequent discoveries laid the foundation for an entirely new branch of physics, one that would ultimately revolutionize our understanding of the microscopic world. The story of the blackbody radiation problem begins in the late 19th century, when scientists were observing the spectrum of radiation emitted by a blackbody, a perfect absorber and emitter of radiation, when it was heated. The classical theories of physics, based on the principles of thermodynamics and electromagnetism, predicted that the intensity of radiation would increase without limit as the frequency of the emitted light increased. This prediction, however, was in stark contrast to what was observed experimentally. In reality, the intensity of radiation increased at lower frequencies, but then dropped off as the frequency increased, particularly in the ultraviolet range. This discrepancy between theory and observation became known as the ultraviolet catastrophe. Classical physics, based on the Rayleigh-Jeans law, was unable to explain why the radiation intensity did not increase indefinitely as predicted. In essence, the laws governing radiation at small scales were not adequately described by classical physics. This failure was one of the most significant unresolved problems of the time and was causing increasing frustration among scientists. Many, including Lord Rayleigh and James Jeans, had tried to solve the problem by extending classical mechanics, but they were met with failure. In 1900, Max Planck was tasked with solving this problem, and in doing so, he would introduce a revolutionary idea. Planck, a German physicist, was at the forefront of theoretical physics at the time, and he approached the issue of blackbody radiation with a fresh perspective. Instead of continuing with classical methods, he turned to a more radical approach that incorporated elements of both classical physics and new concepts. Planck's first step was to reconsider the fundamental assumptions about the behavior of energy. He proposed that energy was not continuous but rather came in discrete packets, or quanta. This idea, which he introduced in his theory of blackbody radiation, marked the first time that the concept of energy quantization was formally introduced into physics. Planck's theory involved the introduction of a new constant, now known as Planck's constant, which would become one of the most fundamental constants in physics. The constant, denoted by h, relates the energy of a quantum to the frequency of radiation. Planck's equation was able to accurately describe the observed spectrum of blackbody radiation by accounting for this quantization of energy. The central idea was that energy could only be emitted or absorbed in discrete amounts, and these amounts were proportional to the frequency of the radiation. The result was a formula that not only solved the ultraviolet catastrophe, but also offered a completely new way of thinking about energy and radiation. Planck's discovery was met with initial skepticism. The idea of energy being quantized was radical and counterintuitive, given the prevailing views of classical physics, which considered energy to be continuous. Planck himself was hesitant to fully embrace the implications of his own work, as he viewed his theory as a mathematical solution to a specific problem rather than a revolutionary new approach to understanding the nature of energy. For Planck, the quantization of energy was simply a mathematical convenience, a tool to make the equations work in a way that matched experimental data. However, as more experiments confirmed his predictions, the full significance of his discovery began to emerge, and Planck realized that he had fundamentally changed the way scientists would think about the universe. The impact of Planck's work was not confined to the problem of blackbody radiation alone. The quantization of energy suggested that the behavior of matter at small scales, particularly at the atomic and subatomic levels, was governed by different laws than those that applied to larger objects. Planck's theory set the stage for the development of quantum mechanics, a branch of physics that would eventually describe the behavior of particles on the smallest scales. The idea that energy is quantized led to the development of key principles such as wave-particle duality, uncertainty, and the probabilistic nature of quantum mechanics. As Planck's work became more widely accepted, other physicists began to build on his ideas. Albert Einstein used the concept of energy quanta to explain the photoelectric effect in 1905, which led to the development of the theory of light as both a wave and a particle. Niels Bohr extended Planck's work by developing a model of the atom in which electrons occupy quantized energy levels. These developments, along with contributions from Werner Heisenberg and Erwin Schrödinger, would ultimately lead to the formalization of quantum mechanics. The consequences of Planck's work extended far beyond theoretical physics and into the realm of practical applications. The discovery of quantization of energy paved the way for the development of technologies such as lasers, semiconductors, and MRI machines, technologies that are now integral parts of modern life. Planck's constant, though an abstract concept, has had profound implications for everything from the design of electronic devices to the study of quantum computing. The mathematical principles that Planck introduced have been applied to fields ranging from material science to cryptography, and the ongoing research into quantum mechanics continues to push the boundaries of what is possible with technology. The development of quantum mechanics, in many ways, represents a break from the deterministic world of classical physics. Planck's work, along with the work of subsequent physicists, revealed that at the atomic and subatomic levels, the behavior of particles is not deterministic but probabilistic. In classical physics, the future of a system could be predicted precisely given enough information about its current state. However, in quantum mechanics, the exact position and momentum of a particle cannot be known simultaneously with absolute certainty, as described by the Heisenberg uncertainty principle. This uncertainty is a fundamental aspect of the quantum world and is a direct consequence of Planck's quantization of energy. Planck's theory also had philosophical implications. The idea that energy is quantized and that the microscopic world operates on fundamentally different principles from the macroscopic world challenged long-held assumptions about the nature of reality. The quantization of energy introduced a level of unpredictability and uncertainty into our understanding of the universe. The classical view of a deterministic, predictable universe was replaced by a quantum view where probabilities and wave functions determined the behavior of particles. This shift had profound implications not only for science, but for our understanding of the nature of knowledge and reality itself. The acceptance of Planck's theory was gradual, as it required a significant shift in the way scientists thought about energy, matter, and the fundamental laws of nature. Initially, Planck's work was viewed with skepticism, and many physicists were reluctant to abandon the classical principles that had served them well for centuries. However, as more experiments confirmed the validity of his ideas, the scientific community began to embrace the new quantum theory. Today, Planck is regarded as one of the founding fathers of quantum mechanics, and his work is recognized as a cornerstone of modern physics. In conclusion, Planck's work on blackbody radiation and his introduction of the concept of energy quantization was a pivotal moment in the history of physics. His theory not only solved the long-standing problem of blackbody radiation, but also laid the groundwork for the development of quantum mechanics. The introduction of energy quanta changed the way scientists thought about energy, matter, and the fundamental laws of nature. Planck's discovery revolutionized our understanding of the microscopic world and has had far-reaching implications for both theoretical and applied physics. His legacy continues to shape the future of science and technology, and his contributions are recognized as one of the most important milestones in the development of modern physics. Max Planck's revolutionary work on blackbody radiation and the introduction of energy quantization had a profound impact on the trajectory of modern physics. The idea that energy exists in discrete units quanta became the cornerstone of quantum theory, setting the stage for the development of quantum mechanics and radically altering the way scientists would understand the microscopic world. Planck's discovery provided the answers to questions that had remained unsolved for centuries, and, though initially met with resistance, his theory slowly transformed the way the scientific community viewed the universe. The blackbody radiation problem, which had remained one of the most puzzling challenges of the 19th century, provided a backdrop for Planck's breakthrough. Classical physics, with its reliance on continuous variables, was unable to account for the behavior of blackbody radiation. This discrepancy, known as the ultraviolet catastrophe, showed that the predictions of classical physics were not valid at high frequencies. The classical theory suggested that the intensity of radiation would increase indefinitely as the frequency increased, which contradicted experimental observations. Planck's genius lay in his ability to recognize that the classical assumptions about energy needed to be reconsidered. He proposed that energy could only be emitted or absorbed in discrete, quantized amounts, which was a radical departure from the continuous nature that classical physics had relied upon. This shift from the continuous to the discrete marked the birth of quantum theory. The significance of Planck's proposal was immense. By introducing the concept of quanta, Planck not only solved the immediate problem of blackbody radiation, but also opened up an entirely new framework for understanding the behavior of energy and matter at microscopic scales. Planck's hypothesis of energy quanta led to a fundamental rethinking of how energy interacts with matter, especially at the atomic level. His introduction of Planck's constant, a fundamental physical constant, became the centerpiece of this new quantum theory, providing a bridge between the classical and quantum worlds. Despite the profound implications of his theory, Planck himself initially viewed his discovery as a mathematical convenience, a temporary solution to the problem at hand. He was reluctant to fully embrace the philosophical and physical implications of quantization, as his view was still rooted in classical physics. Planck did not immediately accept that his theory was truly revolutionary. He thought of it as a way to fit the experimental data within a familiar classical framework. This attitude was common among early pioneers of quantum theory, who often saw their work as incremental steps rather than dramatic paradigm shifts. However, as more evidence accumulated, and as other scientists began to apply Planck's ideas to different problems, the true significance of his work became clear. Albert Einstein, for instance, used Planck's concept of energy quanta to explain the photoelectric effect in 1905, demonstrating that light, long considered a wave phenomenon, also had particle-like properties. This concept of wave-particle duality, which would become one of the central tenets of quantum mechanics, relied on the quantization of energy first proposed by Planck. Planck's work also paved the way for Niels Bohr's development of the model of the atom. Bohr's model, introduced in 1913, was heavily influenced by Planck's quantization of energy. Bohr proposed that electrons in atoms could occupy only certain allowed orbits or energy levels, with energy being emitted or absorbed when an electron moved from one level to another. This was a direct application of Planck's concept of energy quantization in the context of atomic structure, and it was instrumental in the development of quantum mechanics. The impact of Planck's work on the future of physics cannot be overstated. His theory of quantization was the precursor to the formalization of quantum mechanics, which would later be developed by scientists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Quantum mechanics would go on to explain not only the behavior of atoms and subatomic particles, but also phenomena in fields as diverse as condensed matter physics, nuclear physics, and particle physics. Today, quantum mechanics is the foundation of much of modern technology, from semiconductors to lasers to quantum computers. One of the most profound aspects of Planck's discovery was its philosophical implications. The idea that energy is quantized and that the microscopic world operates on fundamentally different principles from the macroscopic world challenged long-held assumptions about the nature of reality. For centuries, the scientific view of the universe was based on the belief that physical properties could be measured and predicted with absolute certainty. Classical physics, especially Newtonian mechanics, was deterministic. The future behavior of a system could be predicted precisely if its initial conditions were known. In contrast, quantum mechanics introduced a probabilistic view of the universe, where the behavior of particles could only be predicted in terms of probabilities, not certainties. This shift to a probabilistic interpretation of nature was one of the key features of quantum mechanics and marked a dramatic departure from the classical world. The notion that particles did not have definite positions or momenta until they were measured, as described by the uncertainty principle, was deeply unsettling to many physicists. It led to debates about the role of the observer in the measurement process and whether the act of observation itself determined the outcome. The probabilistic nature of quantum mechanics is still a topic of philosophical debate and remains one of the most profound and mysterious aspects of the theory. Despite the initial resistance to Planck's ideas, the scientific community gradually embraced his theory. The skepticism that greeted Planck's work was typical of groundbreaking scientific discoveries, especially when they challenged deeply ingrained assumptions. But as the implications of Planck's work became clearer, and as subsequent experiments confirmed his predictions, the theory of quantized energy gained widespread acceptance. By the early 20th century, Planck's work had firmly established itself as the cornerstone of a new era in physics, one that would lead to the development of quantum mechanics. In the years following Planck's discovery, his work began to have far-reaching implications for both theoretical and experimental physics. The development of quantum mechanics led to a deeper understanding of atomic structure, radiation, and the behavior of subatomic particles. The concept of energy quantization also had practical applications, leading to the development of technologies such as semiconductors, lasers, and MRI machines. These technologies, which are now central to modern life, owe their existence to the principles of quantum mechanics that Planck helped establish. The significance of Planck's discovery extended beyond physics and into the realm of technology and industry. Today, quantum mechanics underpins the development of cutting-edge technologies such as quantum computers, which hold the potential to revolutionize fields like cryptography, artificial intelligence, and materials science. The exploration of quantum computing, for instance, is opening up new frontiers in computation that classical computers could never reach. Quantum mechanics continues to inspire new ideas, experiments, and technologies that challenge our understanding of the universe and push the boundaries of what is possible. In conclusion, Max Planck's work on blackbody radiation and his introduction of energy quantization was a breakthrough that reshaped the course of modern science. His theory not only solved the long-standing problem of blackbody radiation, but also laid the groundwork for the development of quantum mechanics, a theory that would revolutionize our understanding of the microscopic world. Planck's discovery altered the way scientists thought about energy, matter, and the fundamental laws of nature, and it continues to influence scientific research and technological innovation to this day. Planck's legacy is a testament to the power of human curiosity and ingenuity, and his work remains one of the most important milestones in the history of physics. The quantum revolution that he began continues to shape the future of science and technology, and his contributions will be remembered as one of the defining achievements of the 20th century. Max Planck's contribution to the development of quantum theory represents one of the most transformative moments in the history of science. His work in 1900 on blackbody radiation and the introduction of the concept of energy quanta fundamentally altered the direction of physics. Planck's discovery not only solved a long-standing problem in theoretical physics, but also opened up a new framework for understanding the behavior of matter and energy at the atomic and subatomic levels. The concept of energy quantization, which was initially met with resistance and skepticism, eventually became the cornerstone of modern quantum mechanics, leading to a new understanding of the very fabric of the universe. The specific problem that Planck sought to address was the issue of blackbody radiation. A blackbody is an idealized object that absorbs all incoming radiation and emits radiation in a way that depends only on its temperature. This radiation spectrum, however, was not understood through classical physics. In the late 19th century, classical physics, based on the laws of thermodynamics and electromagnetism, predicted that the intensity of radiation emitted by a blackbody would increase indefinitely as the frequency of the emitted radiation increased, a result that led to the so-called ultraviolet catastrophe. This prediction was clearly in conflict with experimental observations, which showed that the intensity of radiation increased at lower frequencies and then peaked before decreasing at higher frequencies. This discrepancy between theory and observation remained one of the most perplexing issues in physics at the time. Planck's breakthrough came when he proposed that energy is not continuous but rather exists in discrete units or quanta. This idea was groundbreaking because, at the time, energy was considered to be a continuous variable that could vary smoothly over a range of values. Planck introduced a constant, now known as Planck's constant, which represented the fundamental unit of energy. According to Planck, Energy could only be absorbed or emitted in multiples of this quantum, and the amount of energy was proportional to the frequency of the radiation. This suggestion that energy was quantized was a radical departure from classical ideas and marked the beginning of a new era in physics. The concept of quantization offered a solution to the ultraviolet catastrophe. Planck's theory explained why blackbodies did not emit infinite radiation at high frequencies, as classical theory predicted. Instead, it provided an accurate mathematical description of the observed blackbody spectrum. The success of Planck's formula in fitting experimental data marked a major turning point in physics. While his theory was initially seen as a mathematical trick to explain experimental results, it soon became clear that Planck had stumbled upon a fundamental truth about the nature of energy. Energy was not continuous, as previously thought, but rather existed in discrete packets, and this idea would eventually become the cornerstone of quantum theory. Planck's constant, a seemingly abstract and small number, became one of the most important constants in all of physics. It fundamentally altered how scientists thought about the interaction of matter and energy. His discovery opened the door to a new understanding of the microscopic world, where the laws of classical physics no longer applied. In this new framework, particles and energy behaved in ways that were governed by probabilities rather than certainties, and the rules of classical physics were replaced by those of quantum mechanics. At the time of Planck's discovery, the scientific community was steeped in classical physics, and the idea of energy quantization was met with skepticism. The prevailing view was that energy could take any value within a continuous range. However, Planck's concept of quantized energy was so revolutionary that it challenged the foundations of classical physics. His work laid the groundwork for future developments in quantum mechanics, but it was initially difficult for many physicists to fully accept. Some saw it as a mere mathematical trick, while others rejected it outright because it contradicted the established framework of classical mechanics. Despite the initial resistance to Planck's theory, his work was soon recognized as a major breakthrough. The theoretical foundation he had laid provided the basis for the development of quantum mechanics. Planck's ideas were expanded upon by other physicists, most notably Albert Einstein, who applied the concept of energy quanta to explain the photoelectric effect in 1905. Einstein's work showed that light, which had long been considered a wave, could also exhibit particle-like properties. This discovery was a pivotal moment in the development of quantum theory and marked the beginning of the wave-particle duality concept. Einstein's work, like Planck's, helped to establish that energy and matter are not continuous, but quantized at the microscopic level. Niels Bohr also built on Planck's work by introducing his model of the atom in 1913, which was based on the idea that electrons exist in quantized energy levels around the nucleus. Bohr's model, which successfully explained the spectral lines of hydrogen, was one of the first applications of quantum principles to atomic structure. Bohr's work demonstrated that, just as energy was quantized, so too were the orbits of electrons within an atom. This idea was a direct consequence of Planck's theory and marked the first major step toward the development of quantum mechanics. The development of quantum mechanics was a gradual process, and it took many years before Planck's ideas were fully accepted and understood. As more experimental evidence emerged in support of quantum theory, however, the scientific community began to embrace it. The work of Planck, Einstein, Bohr, and others led to the formulation of a new theory, quantum mechanics, that fundamentally altered our understanding of the physical world. Quantum mechanics provided an entirely new framework for understanding the behavior of particles, energy, and light at the microscopic scale. It replaced the deterministic, predictable laws of classical physics with a probabilistic framework that governed the behavior of particles at the atomic and subatomic levels. Planck's discovery also had profound philosophical implications. The idea that energy is quantized and that the behavior of particles is governed by probabilities rather than certainties raised fundamental questions about the nature of reality. The classical worldview, which had dominated science for centuries, was based on the assumption that the universe operated according to precise laws that could be understood and predicted. In contrast, quantum mechanics introduced a new view of the universe, one that was fundamentally uncertain and probabilistic. This shift in perspective was not only a scientific revolution but also a philosophical one, as it challenged long-held beliefs about the predictability and determinism of the natural world. The implications of Planck's work went far beyond theoretical physics. His discovery of energy quanta led to the development of a wide range of technologies that have become central to modern life. The principles of quantum mechanics are at the heart of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI. These technologies, which rely on the principles of quantum mechanics, have had a transformative impact on fields ranging from electronics to medicine. In addition, quantum mechanics continues to drive cutting-edge research in fields such as quantum computing, which has the potential to revolutionize computing power and solve problems that are currently intractable for classical computers. As we continue to explore the quantum world, the legacy of Max Planck remains profound. His work not only solved a fundamental problem in physics, but also laid the foundation for one of the most important developments in the history of science. Quantum mechanics, born out of Planck's theory of energy quanta, has reshaped our understanding of the universe and has led to the development of technologies that are central to modern life. The world of quantum mechanics, with its strange and counterintuitive principles, continues to inspire new discoveries and breakthroughs, and Max Planck's contribution remains a central part of the scientific legacy that has shaped the modern world. In conclusion, Max Planck's work on blackbody radiation and his introduction of energy quantization marked the beginning of a new era in physics. His theory of quantized energy offered a solution to the blackbody radiation problem and laid the groundwork for the development of quantum mechanics. Though initially met with skepticism, Planck's ideas eventually became the foundation for the quantum revolution, reshaping our understanding of matter, energy, and the fundamental laws of nature. His work has had profound implications for both theoretical physics and practical technologies, and his legacy continues to shape the future of science and technology. Planck's contribution to the development of quantum theory remains one of the most important milestones in the history of physics and continues to inspire scientific research and technological innovation today. Max Planck's foundational work in developing quantum theory is one of the most profound milestones in the history of physics. His discovery of energy quantization was the key to understanding phenomena that classical physics could not explain. Planck's quantum theory not only resolved the problem of blackbody radiation, which had puzzled scientists for decades, but also laid the foundation for what would eventually become quantum mechanics. His work opened the doors to a new understanding of the nature of energy, matter, and the interactions between them on the atomic and subatomic levels. This new framework would lead to the development of technologies that are central to modern life and revolutionize our understanding of the universe. The blackbody radiation problem that Planck sought to address was one of the most significant unresolved issues in physics at the turn of the 20th century. Blackbody radiation refers to the radiation emitted by a perfect absorber and emitter of heat when it is heated. Classical physics, governed by the laws of thermodynamics and electromagnetism, had no explanation for the observed spectrum of radiation emitted by blackbodies at different temperatures. In particular, classical theories predicted that the intensity of radiation would increase indefinitely as the frequency of the emitted radiation increased, resulting in the so-called ultraviolet catastrophe. However, this prediction did not match experimental results. The intensity of radiation actually peaked at a certain frequency and then decreased as the frequency increased, particularly in the ultraviolet range. At this juncture, Planck entered the scene. His approach was initially an attempt to solve a mathematical problem, but ended up unveiling a groundbreaking discovery. Planck proposed that energy is not continuous, but instead comes in discrete units or quanta. This was a radical departure from classical thought, which held that energy could take on any value within a given range. By introducing the concept of energy quanta, Planck was able to explain the observed blackbody radiation spectrum, offering an elegant solution to the ultraviolet catastrophe. He introduced the idea that energy could only be emitted or absorbed in specific, quantized amounts, and the size of these energy quanta was directly proportional to the frequency of the radiation. The introduction of Planck's constant, denoted as h, marked the birth of quantum theory. This constant, which became a cornerstone of quantum mechanics, connected the energy of a quantum to the frequency of the radiation. The formula that Planck derived not only accurately described the observed blackbody spectrum, but also suggested a completely new way of thinking about the relationship between energy and frequency. Planck's equation was able to match experimental data in a way that classical physics could not, and this mathematical breakthrough eventually led to a profound, conceptual shift in physics. The idea that energy was quantized had far-reaching consequences, suggesting that the laws governing the microscopic world were fundamentally different from those that governed the macroscopic world. While Planck's work provided the solution to a specific problem in blackbody radiation, its implications extended far beyond that. The idea of energy quantization opened up new avenues of research and set the stage for the development of quantum mechanics, a new theory that would describe the behavior of matter and energy on the smallest scales. This was a crucial moment in the history of physics, as it provided the first hint that the classical laws of physics, which had been established for centuries, were inadequate to describe the behavior of particles at the atomic and subatomic levels. Planck's work led to the development of a new theoretical framework, quantum mechanics, that would eventually replace classical mechanics for explaining the behavior of microscopic particles. Despite the revolutionary nature of Planck's ideas, they were not immediately accepted. In fact, Planck himself was hesitant to fully embrace the implications of his own discovery. He initially viewed the quantization of energy as a mathematical trick to make the equations work, rather than as a fundamental insight into the nature of reality. Even though his formula provided an accurate description of experimental data, Planck remained skeptical that energy quantization was a true physical principle. Over time, however, experimental results from other scientists, such as Albert Einstein, who applied Planck's ideas to explain the photoelectric effect, helped to solidify the concept of quantization and led to the development of quantum mechanics. As more physicists adopted Planck's quantum theory, its significance became increasingly apparent. The concept of quantized energy became the foundation for the development of quantum mechanics, a theory that would ultimately explain not only the behavior of radiation, but also the properties of atoms, subatomic particles, and even light itself. One of the most important consequences of Planck's work was the development of the idea of wave-particle duality, which would later be championed by Einstein and other physicists. This idea stated that light, which had traditionally been understood as a wave phenomenon, could also behave as a particle, depending on the circumstances. This wave-particle duality, which had profound philosophical and experimental implications, became a central theme in quantum mechanics. The work of Niels Bohr also built on Planck's theory, particularly in the development of the Bohr model of the atom. Bohr's model, introduced in 1913, incorporated the idea of quantized energy levels for electrons orbiting the nucleus. This was a direct application of Planck's idea of energy quanta to the structure of the atom. Bohr's work helped explain the discrete spectral lines observed in atomic emission spectra and was instrumental in the development of quantum theory. The further development of quantum mechanics, led by physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, relied heavily on the foundations laid by Planck. Heisenberg's uncertainty principle for example, which states that the position and momentum of a particle cannot both be precisely determined at the same time, was a direct consequence of the quantization of energy. Schrödinger's wave equation, which describes the behavior of quantum systems, also relied on the concept of energy quantization. These developments ultimately culminated in the formalization of quantum mechanics, which replaced classical physics as the dominant theory for understanding the behavior of particles at the atomic and subatomic levels. The implications of Planck's work went beyond theoretical physics and into the realm of practical applications. The principles of quantum mechanics have led to the development of technologies that have become integral to modern life, including semiconductors, lasers, and medical imaging techniques like magnetic resonance imaging, MRI. Quantum mechanics has also paved the way for the development of quantum computing, which promises to revolutionize the field of computing by solving problems that are currently intractable for classical computers. These advances in technology have had a profound impact on fields ranging from electronics to medicine and beyond, demonstrating the far-reaching practical consequences of Planck's theoretical breakthrough. The philosophical implications of Planck's work were just as profound as the scientific ones. Planck's discovery of energy quantization marked a fundamental shift in how scientists viewed the universe. The deterministic, continuous universe of classical physics was replaced by a probabilistic, uncertain universe governed by the principles of quantum mechanics. This change in perspective had profound implications for our understanding of reality. In classical physics, the universe was seen as a machine governed by precise, predictable laws, but in the quantum world, uncertainty and probability ruled, and the behavior of particles could only be predicted in terms of likelihoods rather than certainties. The uncertainty inherent in quantum mechanics challenged long-standing philosophical assumptions about the nature of reality and our ability to know the world around us. The famous debates between Albert Einstein and Niels Bohr about the nature of quantum mechanics centered around these philosophical implications. Einstein, who had made significant contributions to quantum theory, famously rejected the idea that God played dice with the universe, suggesting that there must be hidden variables that would restore determinism to the theory. Bohr, on the other hand, embraced the inherent uncertainty of quantum mechanics, arguing that it was a fundamental feature of the universe. This debate between determinism and uncertainty, which continues to be explored by physicists and philosophers today, was first sparked by the developments set in motion by Planck's work. The acceptance of Planck's ideas also marked the beginning of a broader shift in the scientific community from classical to modern physics. Classical mechanics, which had been the dominant framework for understanding the physical world for centuries, was replaced by quantum mechanics and relativity, which together form the basis of modern physics. Planck's work not only solved a pressing problem in blackbody radiation but also ushered in a new era of scientific inquiry, one that would continue to expand our understanding of the universe at the smallest scales. Max Planck's work on blackbody radiation and his introduction of energy quantization was a monumental achievement in the history of physics. His discovery not only resolved a long-standing problem but also laid the foundation for the development of quantum mechanics, which has had far-reaching consequences for both theoretical physics and practical technologies. Planck's legacy continues to shape the future of science, technology, and our understanding of the universe itself. His work remains one of the most important milestones in the history of modern physics, and it continues to inspire new generations of scientists as they explore the mysteries of the quantum world. Max Planck's contributions to physics, especially his work in developing the quantum theory, marked a groundbreaking moment in the history of science. The importance of Planck's work cannot be overstated, as his ideas formed the foundation of quantum mechanics, forever changing our understanding of the physical universe. One of the most notable aspects of Planck's discovery was his work on blackbody radiation, which was a key problem that had puzzled scientists for many years. Classical physics, at the time, failed to explain the observed phenomena of radiation emitted by heated objects, specifically blackbodies. The classical theory predicted that intensity would increase infinitely at higher frequencies, but this was not observed experimentally. Planck introduced the concept of energy quanta to explain this discrepancy, revolutionizing our understanding of energy. Before Planck, the prevailing theory of radiation was based on classical physics, which described energy as a continuous quantity. However, Planck's work suggested that energy was not continuous but instead came in small, discrete units. He introduced the idea that energy could only be emitted or absorbed in fixed quantities, or quanta. This concept was a fundamental shift in how energy and matter were understood. Planck's introduction of this idea, while initially controversial, opened the door to the quantum theory. His formulation of a mathematical expression for blackbody radiation explained why objects emit radiation in a particular way and why intensity peaks at certain frequencies and decreases thereafter, which classical physics could not account for. Another crucial point of Planck's work was the introduction of Planck's constant, a fundamental physical constant that linked energy to frequency. Planck's constant, denoted by h, became one of the cornerstones of quantum theory. This constant defined the smallest possible unit of energy that could be transferred or absorbed. It had profound implications, serving as the foundation for future developments in quantum mechanics. This concept not only allowed Planck to resolve the blackbody radiation problem, but also paved the way for the later work of other scientists, such as Albert Einstein, who used Planck's quantization of energy to explain the photoelectric effect, and Niels Bohr, who applied it to his atomic model. Planck's ideas also marked a significant departure from classical, deterministic views of the universe. Classical physics, especially Newtonian mechanics, operated on the assumption that the behavior of objects could be predicted with perfect accuracy, provided the initial conditions were known. In contrast, quantum mechanics, influenced by Planck's theory, introduced a probabilistic view of nature. The behavior of subatomic particles could no longer be precisely determined, but was instead described by probabilities. This shift was fundamental to the development of quantum mechanics, which replaced classical mechanics as the framework for understanding atomic and subatomic phenomena. This change in perspective had far-reaching philosophical implications, challenging long-held beliefs about the determinism of the universe. In the broader scope of science and technology, Planck's work had a lasting impact. The principles of quantum mechanics, developed from Planck's initial theories, led to the invention of technologies that have transformed modern life. Semiconductors, lasers, and MRI machines are just a few examples of how quantum mechanics, rooted in Planck's ideas, has enabled technological advances. In addition, the ongoing research into quantum computing, which promises to revolutionize fields such as cryptography and artificial intelligence, continues to be shaped by Planck's original contributions. His work was not merely theoretical but has practical applications that impact technology, medicine, and other fields. Through his introduction of quantization and Planck's constant, he provided the conceptual tools that would go on to transform both science and industry. Planck's legacy continues to shape the future of scientific exploration and technological innovation. Max Planck's groundbreaking discovery of energy quantization laid the foundation for quantum theory, which would go on to revolutionize modern physics. His exploration into the problem of blackbody radiation provided a breakthrough that not only solved a long-standing issue in physics, but also opened the door to a new understanding of energy, matter, and the universe itself. One of the key aspects of Planck's work was his introduction of the concept that energy is not continuous, but comes in discrete packets or quanta. Prior to Planck's work, the prevailing belief in classical physics was that energy could vary continuously and the idea of discrete energy levels was unthinkable. However, Planck's theory showed that energy could only be absorbed or emitted in fixed amounts proportional to the frequency of the radiation. This insight was revolutionary and set the stage for the quantum mechanics that would follow. Another critical element of Planck's theory was the formulation of Planck's constant, a physical constant that defines the smallest possible unit of energy. Planck's constant, denoted by h, became the cornerstone of quantum mechanics, serving as the link between energy and frequency. The introduction of this constant was key because it gave scientists a concrete, measurable value that would apply to a range of phenomena. It not only resolved the blackbody radiation problem, but also played a central role in the work of other physicists, such as Albert Einstein and Niels Bohr, who built upon Planck's ideas to further develop quantum theory. The constant allowed for the accurate calculation of energy levels in atomic systems and contributed to the conceptualization of quantum mechanics as a probabilistic theory rather than a deterministic one. The third pivotal aspect of Planck's work was its radical departure from classical physics. Classical mechanics, which had been the dominant theory of physics for centuries, was based on the idea that the universe operated in a predictable, deterministic manner and that objects followed well-defined paths. Planck's discovery of quantized energy introduced a probabilistic approach to understanding subatomic phenomena. In the quantum world, particles such as electrons did not have definite positions or speeds, but instead existed in a state of probability, with only the likelihood of a particle being found in a given location or state. This shift from a deterministic to a probabilistic view of the universe marked the beginning of quantum mechanics and challenged the very core of classical physics. One of the most significant consequences of Planck's work was the development of the theory of wave-particle duality. Planck's quantization of energy set the stage for Albert Einstein's explanation of the photoelectric effect, in which light was shown to behave both as a wave and as a particle. This idea, initially proposed by Einstein in 1905, was a direct extension of Planck's concept of quantized energy. Wave-particle duality became one of the central tenets of quantum mechanics, as it showed that particles like electrons and photons could exhibit both particle-like and wave-like behaviors depending on the circumstances. This concept, which became integral to quantum theory, demonstrated the deep connection between the properties of light and matter, a connection that classical physics had failed to explain. Lastly, Planck's work laid the groundwork for technological advancements that have since become integral to modern life. The principles of quantum mechanics, which arose directly from his work, are the basis for technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI. Semiconductors, for example, rely on the quantum mechanics of energy levels to function, allowing for the development of modern electronics such as computers and smartphones. Lasers, which are a direct application of quantum theory, have become essential in fields ranging from telecommunications to medicine. MRI technology, which has revolutionized medical imaging, is based on quantum mechanical principles as well. These applications highlight how Planck's abstract theoretical work laid the foundation for a technological revolution, demonstrating the far-reaching and practical impact of quantum mechanics. In conclusion, Max Planck's introduction of energy quantization and his development of Planck's constant were pivotal in the creation of quantum theory. His work challenged classical physics, providing the key insight that energy is not continuous, but exists in discrete packets, or quanta. This breakthrough led to the development of quantum mechanics, which not only altered our understanding of the subatomic world, but also paved the way for technological innovations that continue to shape the modern world. Planck's legacy is one of profound significance, marking a turning point in the history of physics and providing the theoretical tools that have driven the development of numerous modern technologies. Max Planck's introduction of energy quantization and his subsequent development of the quantum theory marked one of the most transformative shifts in the history of physics. Planck's work began with the problem of blackbody radiation, a phenomenon that classical physics struggled to explain. The classical theory predicted that a perfect blackbody would emit an infinite amount of radiation at short wavelengths, particularly in the ultraviolet spectrum. This prediction, known as the ultraviolet catastrophe, contradicted experimental observations where the intensity of radiation actually peaked at a certain frequency and then decreased as the frequency increased. This discrepancy became one of the most significant unresolved problems in physics. Planck's insight, however, led to a groundbreaking resolution. By proposing that energy could only be emitted or absorbed in discrete packets, or quanta, he was able to explain the observed radiation spectrum and solve the long-standing problem. The introduction of Planck's constant, a fundamental constant of nature, was another critical component of his theory. Planck's constant, denoted by h, links the energy of a quantum to the frequency of the radiation. The formula that Planck developed, which included this constant, was able to accurately describe the observed spectrum of radiation emitted by a blackbody. While the concept of energy quantization was initially seen as a mathematical trick, Planck's discovery soon gained broader recognition as the foundation for a new era in physics. The constant itself, though small in magnitude, has since become one of the most important numbers in physics, central to the development of quantum mechanics and modern science as a whole. Planck's work also represented a dramatic departure from classical physics, which had dominated scientific thought for centuries. Classical physics operated on the assumption that physical quantities, such as energy, could vary continuously. The quantization of energy challenged this idea by suggesting that energy could only exist in discrete values based on the frequency of radiation. This departure from the classical worldview opened the door to the development of quantum mechanics, which would go on to replace classical physics as the framework for understanding atomic and subatomic phenomena. In the quantum world, particles do not follow smooth, predictable paths, but instead exist in states of probability, with their behavior governed by wave functions rather than deterministic laws. The concept of wave-particle duality, a central principle of quantum mechanics, was closely tied to Planck's work. Though Planck initially applied his theory to explain blackbody radiation, his work laid the foundation for later developments that would introduce the dual nature of light. In 1905, Albert Einstein used Planck's concept of quantized energy to explain the photoelectric effect, showing that light behaves not just as a wave, but also as a particle, a concept that became a cornerstone of quantum mechanics. This wave-particle duality extended to all particles, suggesting that both light and matter exhibit characteristics of both waves and particles. The understanding of this duality was crucial to the development of quantum mechanics and helped shape the way scientists think about the behavior of particles and energy. Furthermore, Planck's work sparked a fundamental shift in our understanding of uncertainty and measurement in the physical world. In the classical world, precise measurements could, in principle, be made with absolute accuracy, and the behavior of systems could be predicted with certainty. Quantum mechanics, however, introduced an inherent uncertainty into the equation. This uncertainty, famously formulated in Heisenberg's uncertainty principle, asserts that it is impossible to precisely measure both the position and momentum of a particle simultaneously. This uncertainty was a direct consequence of the quantization of energy, which Planck had introduced. The notion of uncertainty fundamentally altered the way scientists thought about the world, leading to new philosophical questions about the limits of human knowledge and the nature of reality itself. The legacy of Planck's work extended far beyond the theoretical realm, with direct practical applications emerging from the principles of quantum mechanics. Technologies such as semiconductors, lasers, and magnetic resonance imaging (MRI) have all been made possible by quantum mechanics, which is rooted in Planck's foundational theories. In the case of semiconductors, for example, quantum mechanics describes how electrons behave in materials, making it possible to design and manufacture computer chips. Lasers, which rely on the principles of quantum mechanics, are now integral to fields ranging from telecommunications to medicine. MRI, which is used in medical imaging, also relies on quantum principles to produce detailed images of the human body. These technologies, all rooted in Planck's discoveries, have revolutionized numerous industries, demonstrating the far-reaching and lasting impact of his work. In conclusion, Max Planck's work on blackbody radiation and the introduction of energy quantization represents a watershed moment in the history of physics. His ideas not only resolved a major problem in classical physics but also opened the door to the quantum revolution. Planck's constant, the core of his theory, became a fundamental part of the quantum mechanical framework that would replace classical physics as the dominant theory in understanding the universe at the atomic and subatomic levels. The development of quantum mechanics and the discovery of wave-particle duality were direct extensions of Planck's work, reshaping our understanding of energy, matter, and the fundamental laws of nature. Planck's contributions have had profound philosophical and technological implications, shaping the modern world in ways that continue to impact both science and society. Max Planck's contributions to physics, particularly his formulation of quantum theory, revolutionized our understanding of energy, matter, and the underlying laws of nature. His groundbreaking work in 1900, specifically regarding blackbody radiation, solved a critical problem in classical physics and laid the foundation for the entire quantum revolution. The classical theory of blackbody radiation predicted that a heated object would emit infinite energy at high frequencies, a result known as the ultraviolet catastrophe. This prediction, however, contradicted experimental observations, which showed that the intensity of radiation actually peaked at a specific frequency and then decreased. Planck's insight was the introduction of the idea that energy is not continuous, as classical physics assumed, but instead comes in discrete packets, or quanta. This theory was revolutionary, offering a solution to the blackbody radiation problem and marking the birth of quantum theory. Planck's concept of quantization of energy laid the groundwork for what would later become quantum mechanics. According to Planck, energy could only be emitted or absorbed in fixed quantities, and the amount of energy was directly proportional to the frequency of the radiation. This was a radical departure from classical physics, which treated energy as a continuous variable that could vary smoothly. By introducing this quantization, Planck was able to resolve the discrepancy between theory and experiment that had baffled scientists for years. His mathematical expression, known as Planck's law, accurately described the observed radiation spectrum, thus providing the first successful explanation of blackbody radiation. A central aspect of Planck's theory was his introduction of Planck's constant, denoted by h. Planck's constant became a fundamental constant in physics, representing the relationship between energy and frequency. This constant defined the smallest possible unit of energy that could be transferred or absorbed, and its introduction marked a major shift in scientific thinking. Planck's constant became the cornerstone of quantum mechanics, and its significance was later recognized by other key physicists, including Albert Einstein and Niels Bohr. It was Einstein who, in 1905, extended Planck's quantization concept to explain the photoelectric effect, further cementing the validity of Planck's theory and contributing to the establishment of quantum theory. Planck's ideas also led to a fundamental shift in how scientists viewed the nature of reality. Classical physics, which had dominated science for centuries, was based on the assumption that the universe was deterministic and that the behavior of objects could be precisely predicted given enough information. Planck's work, along with the subsequent developments in quantum theory, introduced an element of uncertainty into the understanding of the physical world. In the quantum world, particles and energy behaved in probabilistic ways rather than following deterministic paths. This shift from certainty to probability would later be encapsulated by Werner Heisenberg's uncertainty principle and become a core feature of quantum mechanics. Planck's work also contributed to the development of wave-particle duality, a key concept in quantum mechanics. The idea that light and matter could exhibit both wave-like and particle-like properties was a direct extension of Planck's theory. In 1905, Albert Einstein used Planck's concept of quantized energy to explain the photoelectric effect, where light, traditionally understood as a wave, was shown to behave as a particle in certain conditions. This duality, in which light could exhibit both wave-like and particle-like properties, became one of the central principles of quantum mechanics and a defining feature of the quantum world. It was later expanded upon by other physicists like Louis de Broglie and Niels Bohr, further solidifying the concept of wave-particle duality. Another significant aspect of Planck's theory was its impact on the philosophical interpretation of science. The shift from classical physics to quantum mechanics forced scientists to rethink the very nature of the universe. In classical physics, the universe was seen as a machine governed by precise, predictable laws. However, in quantum mechanics, the universe was revealed to be far more uncertain and probabilistic, where the act of measurement itself could influence the outcome. This challenge to determinism sparked philosophical debates about the nature of reality, knowledge, and the role of the observer in shaping the universe. The philosophical implications of quantum mechanics are still debated today, and Planck's work was instrumental in ushering in this new, more complex understanding of the world. The influence of Planck's work extended beyond theoretical physics and into the realm of technology. Quantum mechanics, which arose from Planck's ideas, has become the foundation for numerous technologies that are now central to modern life. Semiconductors, lasers, and magnetic resonance imaging (MRI) machines are just a few examples of how quantum principles have been harnessed for practical applications. The development of quantum mechanics has also paved the way for cutting-edge technologies like quantum computing, which has the potential to revolutionize industries by solving problems that are currently intractable for classical computers. These advancements show the far-reaching impact of Planck's work, from the laboratory to the marketplace. In conclusion, Max Planck's contributions to physics represent a monumental shift in the way we understand the universe. His introduction of energy quantization, along with the development of Planck's constant, solved the long-standing problem of black-body radiation and laid the foundation for the development of quantum mechanics. His work marked the beginning of a new era in physics, where the deterministic laws of classical physics gave way to a probabilistic and uncertain view of the microscopic world. Planck's theory also paved the way for technologies that have become integral to modern life, demonstrating the profound impact of his work on both science and society. Through his pioneering contributions, Max Planck helped to shape the course of modern physics and set the stage for the quantum revolution.